Thank you very much. My name is Yared Desta. Currently, I'm pursuing my PhD at Lodz University of Technology in Poland. And it's a great opportunity to participate in International Conference on Nonlinear Science and Complexity 2024 under the testing and identification of mechatronic system with nonlinearities. So the title that I'll be sharing with you today is Design, CFD Simulation, Fabrication and Experimental Testing of Three-Wheeler Vehicle Muffler for Noise Attenuation. The contents that I'll be discussing are introduction, general and specific objective, design, CFD simulation, experimental and the transmission loss analysis, and finally, conclusion. The introduction part, a muffler is a device that reduces the noise produced by an internal combustion engine, and there would be an intolerable amount of exhaust noise in our surrounding environment if automobiles did not have mufflers. So mufflers are crucial in minimizing exhaust system noise. And the selection of mufflers depends on the type of the vehicle. Generally, mufflers are classified into two, passive and active mufflers. Passive mufflers can be classified into three, reactive, observative, and hybrid type of mufflers. The main significance of the study is to reduce the noise level in the environment, as well as to give a comfort for passengers during a ride. This type of vehicles are actually manufactured in a Ford company in India. They are noisy due to the engine and due to the arrangement or the configuration of the mufflers. Therefore, the design of muffler that's why the design of muffler is required. So these types of vehicles are common in African countries. They mostly use as a transportation mechanism. So to mention types of muffler, we have here active types of muffler, reactive types of muffler, and observative types of muffler. Since this three-wheeler vehicle muffler, in this case, uses these reactive types of muffler, what makes this different from the other is that it has different classes inside in which the sound cancellation occurs. So these are designed accordingly due to the design parameters. So this is the type of muffler. So I'll be discussing this muffler. So the general objective is, as I've mentioned in my title, is actually to carry out the design, CFD simulation, fabrication of this three-wheeler vehicle muffler for noise reduction. The specific objectives are to model the existing and design muffler using a full-line tool, to investigate the current muffler, which is done both experimental and simulation, to evaluate the transmission loss using COMSOL multiphysics, which is COMSOL multiphysics is analysis software actually used for coupling of different phenomena, and to study the exhaust gas velocity and pressure graphs. So I'll be discussing these parts in the next slide. So now I'm going to discuss the performance parameters for mufflers. So there are a lot of performance parameters, but the main are the transmission loss, insertion loss, the back pressure, and the sound pressure levels. So since this design is mainly based on the transmission loss and the back pressure, the transmission loss is the difference between the acoustic energy of the forward moving wave at the muffler's input and the forward moving transmitter wave at the outlet. This is known as the transmission loss, and the opposite is the insertion loss. Transmission loss can be described mathematically. It can be measured by actually in decibel. For instance, this is just a simple types of muffler, one inlet and one outlet. At the inlet, we have the incident wave, the sound wave, and then we have the transmitting wave, we have the reflected wave. So the transmission loss is equals to the 10 logarithm of the incident wave divided by the transmission loss. The opposite of the transmission loss is actually the insertion loss. So the engine specification for this vehicle is a four-stroke, a single cylinder. This vehicle is common in Africa, and the model is four-stroke, single cylinder. Maximum torque is 28 Newton meter at this range, and the maximum output power is 7.2 kilowatts, ISO standard, and the capacity is 499 cc, and it is the cylinder dimension. So this is the comparison of the dimension of the existing muffler and the design muffler. We have some changes here. The minor diameter, since it is spherical shape, and the existing one is 8, and the design one is actually 10, and the major diameter is 18. In the same, we have other parameters are almost the same, but we have the length difference in the existing, which is 42, and the 45. Other parameters are constant. So this is the initial boundary condition for the analysis of the ANSYS simulation. As we have the area, we have the viscous enthalpy, density, viscosity, temperature value, and the initial velocity that is selected is 60 meter per second. So for the timing, let me discuss the geometry. The geometry of the existing muffler is looks like this, and this one is for the designed muffler. It has one inlet and one outlet. Similarly, for the design muffler, it has one inlet and one outlet. This is the internal or the inner view of the existing muffler. How it works, we have this part is connected with the engine. Since muffler is the last component of the engine, the exhaust system. Therefore, when the gas comes out from the engine, goes in through the inlet, and we have the perforation here, and it's the gas gets out, sprays out through this perforation. So there is a noise cancellation occurs in between this baffles, and finally, due to the pressure difference, the gas gets out from the first chamber to moves back to the second, back to the second chamber, and circulates here and gets into this perforated area, and it goes out through this pipe. And it's similar, but what makes the first one, the existing muffler, different from the design one is that this has the modification that's made by increasing the chamber. We have the chamber. In this case, we have the 3 section, but in this case, the design case, we have 4 classes. So this is the difference, and there is a design configuration is also different. So this is the mesh result. And the mesh result, and this shows the quality of the mesh. And moving on to the pressure analysis of the simulation. And this is the existing muffler. It has 3 chamber, and this one is the design muffler. It has 4 chamber. So this the color shows the result of the colors shows the pressure results in the left side. At the right side, we have around 32,590 at the inlet, and at the exit is around the outlet pressure is 5,695. Similarly, the inlet pressure for the design one is also depicted here. And this shows that if we take the difference of this to calculate the pressure drop, since we have the inlet pressure and the outlet pressure, taking the difference and dividing by the inlet pressure, we have the 82.5% pressure drop in the existing muffler. Whereas in the design muffler, we have 92.3% pressure drop. So moving on to the velocity analysis of this one is the existing, and on this side, the right side is the design muffler. In the velocity analysis, as I have said before, this part shows the value of each color in here. So as we can see at the inlet part, it starts from 60 meters per second. Once the gas sprays out through these perforated holes, we have just a fire-like thing, as we can see from clearly seen from the area, and it's due to the pressure difference. It circulates here, and the gas still looks for the low pressure area. So when it gets into the second chamber, the second pipe, as we can see here, we have the change in the color. When it gets out, we have also the result, the value in the left side. This the below is directly shows the 2D velocity magnitude position graph of the above velocity analysis. So this is similarly for the velocity, the cut plot for the designed muffler. And this one is the velocity magnitude versus the position graph. moving on to the COMSOL multiphysics analysis of the transmission loss. We have here we measured the transmission loss. Therefore, at the inlet we have the noise level is around 90 decibel, but at the exit the main part is required is releasing the exit the noise. Therefore, at the exit we have the value between 30 and 40. But in the design muffler at the inlet, we have 90, but at the exit, the color, as we can see, it is between 20 and 0 value. Therefore, this, and from the result that I got, the design muffler has reduced the amount of noise by 15 decibel. So in the COMSOL multiphysics analysis of the transmission loss graph, we have the graphs generated from that analysis. So this is for the existing muffler, and this one is for the design muffler. This graph is actually plotted for the frequency range from 1 to 1,500. So in the existing muffler, as we can see, the maximum transmission loss is 60, whereas in the second case, we have in the design model, we get 75. If we take the difference, we have 15 decibel difference. So if you see each point, the designed muffler shows a better transmission loss result. The higher the transmission loss means the higher the back pressure, but the lower the noise. So our main requirement is reducing the noise by also taking account other parameters like the back pressure, the sound pressure level, and the insertion loss. So we have the result, which is obtained from the experimental value. In the full throttle of the sound pressure level of full throttle position, we have the sound pressure level that is measured in the existing muffler is 85.3 decibel, whereas in the designed, which is 71.9 decibel. This shows that the noise or the acoustic pressure level at the existing muffler. This one is the acoustic pressure level for the designed muffler. We have the minimum values, we have the average value of the noise, we have maximum values of the noise. So moving on to the conclusion, just due to the timing, the design model was more successful actually in the lowering exhaust pressure than the existing model. So as we have seen that the exhaust pressure in the designed is around 92.3% pressure drop, but in the existing model, the pressure drop is 82.5%. So this is all about my presentation. So if you have any question, please. Thank you very much.